Hello everyone, this is Guthrie and I am in Lausanne. In this video, I'd like to talk about our linear system project. So in the project, we use the Lego part blocks to build out the mass damping spring system. And after that, we use the sensor and the Arduino software to record the displacement versus a time graph by putting the mass and release at different position. We can adjust the mass by adding the block and adjust the value of C and K by adding the rubber band and also adjust the tightness of the string. So after we record all the data, we need to derive the time domain position response. Since the system is the underdamping system, the mass is oscillating at the beginning and come to the rest at the end. So we can use the Laplace and the inverse Laplace transform to obtain the functional cosine. And it should be noticed that the initial condition is need to consider when we do the Laplace and inverse Laplace transform because the position is not zero when the t is equal to zero. And we can use the MATLAB code to appeal to plot the graph by our time domain position response. And also we can use the MATLAB code to compute the ODE and then plot the graph. So the graph from the ODE is the same to the graph of the time domain position response. So the graph from the MATLAB is similar to the graph that recorded by the Arduino sensor. What's more, we found that how MCK affect the value of the natural frequency and the damping ratio. So natural frequency is like the friction. Once we increase the mass or something else to smaller the natural frequency, the larger friction will bring shorter frequency. So the damping ratio will affect the overshoots, uh, which determine how fast the oscillation decay from one bounce to the next. So the overshoot will be the largest when the damping ratio is close to zero.
So my name is Zhou Sumeng, and I will have an introduction to the poles of the system. So the poles in transfer function provide crucial information about the system's behavior, stability, and the response to the input. So here we provide the code in MATLAB to how to get the poles. So first we need to get the transfer function by getting three constant value, m, c, and k. So after getting the transfer function, we can easily get the result of the poles. We also provide the basic formula to calculate the poles, which is shown by the picture below. So in this slide, you will see how the poles will determine a system in the experiment. So here we have two examples, which are the transfer function we simulate from the experimental result. So we can see both of them are on the damping response. Notice that the damping ratio for on the damping system is less than 1 but greater than 0. It determines the amount of damping in the system and influence the amplitude of the oscillation and the speed of reaching the steady state. We can also calculate the rising time, peak time, and the settling time for on the damping system. So in conclusion, the pose of the system shows the system is on the damped system, which means the elevator will finally goes to a constant position. So next I will talk about the transfer function. From the graph provided on the left, we can see if the imagery part of the pose goes to more left, the system will be more stable. The transfer function we simulate can follow the rule and it reflects the real motion of the elevator. And I also want to talk about some limitation for this experiment. The most important one is the data accuracy. So the prices and accurate data from a Lego elevator experiment might be challenging due to the limitation in measurement equipment and the error of sensor feedback. So this could affect the reliability of the data used to identify and model the transfer function.